Okay, so let's talk about Chapter 29, Introduction to Quantum Mechanics. So we're going to talk about the quantization of energy, the photoelectric effect, how the E&M spectrum is related to the photon energies, and then specifically how we get momentum for a photon. So the idea with quantum mechanics is that the fundamental unit of energy is Planck's constant, h, or h bar as I drew it there. And we needed a new theory to explain what was going on when we were studying the behavior of electrons. When we decided to create quantum mechanics out of necessity, one of the foundational principles of quantum mechanics states that whatever the theory is, there must be some correspondence between the very small and the very large. So there must be a limit as we make our system larger and larger. The quantum physics, the theory of quantum mechanics should approach the theory of classical physics. So that was one of the charges of the founders of quantum mechanics was, can you come up with a theory which in the limit of large numbers approaches classical physics? So that term is called the correspondence principle, and that principle is dependent on the desires of the founders of the theory. So the quantization of energy is that trying to explain the emissions of black bodies. So black body is a key word here, and when you heat something up, it emits light, and the spectrum of light, the intensity versus wavelength has a very specific shape. It looks like these kind of purple lines here. So the hotter it gets, the more it shifts to the blue. The peak value shifts, and it follows kind of this curve like that for the peak values. So a very hot thing would be white hot. A very cool thing would be red hot. And let's see. Yep, and so in order to explain blackbody radiation, in order to explain this, Max Planck came up with this formula where the fundamental unit of energy is Planck's constant, h. He wasn't super happy with this, but he ended up using this and then saying, you know, like, hey, this is what I came up with. I'm not so confident in it, but it makes the theory work. I can predict any spectrum for any temperature thing without having to do anything. So let's see, there he is. Okay, so the main reason for coming up with this theory of quantum mechanics was to try and explain, as we'll see in the next few chapters, the emission lines of different gases. So this thing here is called the atomic spectra, and basically when you heat a gas up, it emits colors, not continuous spectra. This is a continuous spectra here. Continuous because it emits, it's emitting all wavelengths, but varying amounts, but it's continuous. It's emitting every wavelength of light. And this would be the visible spectrum into here, but you've got infrared and ultraviolet on the other side there. So in order to try to explain emission spectra, which are quantized, we needed, and by quantized I mean, look at this green line, another greenish line, yellow line. It's not a pure rainbow, it's very specific lines there. This spectra, where it comes from, is you take a nice gas and you light it up, and then you put a prism, and then the light gets split into its various colors by the prism. And what you see is you don't see a full rainbow, you see these emission spectra. And the energy levels that create these colors are in units of Planck's constant. So anyway, okay, so 29.2. So 29.1 is just kind of giving you an introduction of why we need quantum mechanics and what it actually does. It allows us to explain blackbody radiation and emission spectra of atoms, which we'll talk about later. Okay, the photoelectric effect says, and this is what Einstein got his Nobel Prize for, not any of his relativity stuff, if you can believe that, but just for the photoelectric effect, which ultimately did help create the quantum mechanics as a theory too. So the photoelectric effect says that the energy of a photon is proportional to its frequency times Planck's constant. Okay, what that predicts is that as you go up to higher frequencies, you're going to have more energy. Whereas classical theory predicts that if you have more photons or a brighter light, you'd have more energy. Well, it turns out Einstein was correct. The energy of light depends on its frequency. And so if you were to shine green light at something and red light at something, the green light might actually make it do something. The red light won't, because the green light has more energy since it's a shorter wavelength light. Okay, so there is a certain amount of energy called the binding energy in a material that keeps an electron in it. So let's say I have a surface and there's some electrons floating around near the surface, and then I shoot some light at it. If I shoot some light at it, if it has enough energy, it can knock an electron right out of there. The energy required to knock an electron out of the atom is equal to the binding energy of the material, and it depends on the material. And this is called the work function of the material, written as sometimes phi, sometimes as W, sometimes called the binding energy, Be. So when you're calculating the work function, or sorry, calculating the energy necessary to knock an electron out of something, what you're going to do is someone's going to give you the work function for a material, and then you set that equal to HF, divide by H, and you'll be able to calculate the threshold frequency to knock an electron out. Once you knock an electron out, once you overcome the energy, the binding energy, if you take the energy of your photon minus the binding energy, whatever's left will be the kinetic energy of the electron, and you can set that equal to 1/2 mass electron v squared, and you can actually solve for the velocity of the electron that's kicked out, and that could be useful in certain situations. Okay, so here you go. You've got your kinetic energy versus frequency. Until you get to that fundamental frequency, boing, the electron doesn't get kicked out of the material until that fundamental frequency is reached. Okay, so yeah, we get an example here. What's the energy for a photon with 420 nanometers? It's just E equals HF. Frequency is this. Frequency is C over lambda. So your equation becomes energy equals HC over lambda, and C is the speed of light. Lambda is 420 times 10 to the minus 9 meters. So you can just plug those values in, and you get that the number of joules is this, and then you know that there's 1 electron volt per 1 times 10 to the minus 19 joules. So you get about 3 electron volts for the energy of 420 nanometer light. And part B says, what is the maximum kinetic energy if you shoot 420 nanometer light at calcium, given that the work energy is 2.71 electron volts for calcium? Well, so you already know you've got 2.96 electron volts available to you, minus 2.71, so you're going to have some energy left over, and that energy that's left over is 0.246 electron volts. Okay, and that's what's left over. And then if you wanted to calculate the velocity, you could set that equal to 1/2 mv squared, and then solve for the velocity. All right, so 29.3. This is just the full spectrum of the light, full thing. And so we're on the visible light's on the order of a few electron volts. When you get into ultraviolet and X-rays and gamma rays, you're going up by a factor of 1,000 each time. So 40 electron volts up to 4,000 electron volts up to 4 million electron volts. And then infrared is the opposite direction. You can go down to 1/10 of an electron volt to 100,000th of an electron volt to 1 billionth of an electron volt, and so on, just to give you some ideas of some energies. This is pretty cool. That's an X-ray. That's so cool. He did an X-ray of his wife. She got dosed with a lot of radiation. All right. This is just showing you how X-ray tubes work. You put electrons up to a very high energy. If it hits the target with enough energy, it can knock photons out at very high energies, and that's how you generate X-rays in like an X-ray machine at the dentist's office or in the hospital. Okay, we've got this X-ray versus frequency here for your general spectrum coming off an X-ray tube. There's these two features which we'll talk about later. We call them the characteristic X-rays, and it comes from a couple of the special orbitals of the electrons, which are material dependent. So we'll talk about those when we talk about the atomic structure in a couple of chapters here. But Bremsstrahlung stands for breaking radiation here, and breaking radiation is this when you slow an electron down, you're going to have the energy, the electron is going to have some energy, you're going to subtract off some kinetic energy off of it, and this kinetic energy that's lost is turned into a photon with whatever the energy is of that kinetic energy change. So you're going to change the kinetic energy of an electron by slowing it down. However much energy you take from the electron, it will emit that same energy in the form of light, and we call that Bremsstrahlung radiation. And that's why it's a distribution like this. It's not a fixed value, it's a distribution. These other two spikes here come from specific properties of the material. Okay, so blah, blah, blah. Yeah, okay, this example's not too great. Visible light there. Blah, blah, blah. Let's see this. Nope, it's fine. So infrared radiation, microwaves, they have the lowest energies. They have almost no energy. So read that stuff for your information. That's good. Okay, 29.4. The photon itself has momentum, which is a very interesting thing. The formula given by momentum is P equals h over lambda. And you get that from assuming that the energy E equals P squared C squared plus M squared C to the fourth. If you assume zero mass, then you have the energy of E squared equals this. So you have the energy is equal to PC of a photon, so P equals energy over C, and the energy is HF over C, and F is 1 over lambda with a C in there, and then you can get this rid of the C, and let me erase all this, and so that's how you end up with this formula that P equals h over lambda. So if you want to know what is the momentum of a photon with 500 nanometers, Planck's constant divided by 500 nanometers gives you the momentum, kilogram meters per second, of that photon. So even though the photon has no mass, when it knocks into something, it can bump it around because it has an intrinsic momentum. Let's see. So yeah, if you were to take that momentum and give it to an electron, the electron would travel about 1,460 meters per second, which is kind of cool. Blah, blah, blah. And so yeah, here's a great example. There's a example of using a solar sail that the sunlight will apply pressure to it. You can see there's a few folks here trying to design this thing and test it out. Space sails is what they're called. And we can use them to travel far distances because the sun will constantly apply pressure to it, so you'll have sort of a constant acceleration. Here's your relativistic photon momentum. You have the full relativistic equation here, but we assume the mass is 0, but the P isn't, so we have this relationship E equals PC. It's a little bit of a cop-out, but let's see what happens. P equals E over C. E is hc over lambda over C, and so you have h over lambda there, and so you get this P equals E over C, or P is h over lambda, and both those things give you the energy of or the momentum of a photon. Okay, see you next time.